Yeah, so we talked about the two main kinds of digital filters, the feed-forward and the feedback filters, and their representation as a difference equation, or in the block diagram. So these all say the same thing, it's just different ways of looking at it. And the feed-forward filter has the basic idea of taking one portion of the input signal and putting it into a delay for a certain number of samples, adding it back to the original input signal. That gives the output. A feedback filter, you instead take a portion of the output signal, put that one into the delay, and feed that to the input signal. Now these two also have different names, and that has to do with their impulse responses. So this one is a finite impulse response filter, a FIR filter, whereas this one has an infinite impulse response. And what is an impulse response? Well, shortly speaking, you can say that you can use an impulse such as a very brief audio signal in order to get an idea of what a room or a filter or an effect or something is doing to the signal. And by definition, the unit impulse, called delta n, is a function that has 1 at time 0 and otherwise only zeros. So let's see if this actually has a finite, an ending impulse response. We put the delta function into it and see what happens. I'm going to remove the block diagram, but we have the representation above here. So, y at time 0 is now half the input signal at time 0, which is 1, plus half the previous sample, which is 0. So y at time 0 is 1/2. Y at sample 1 is half 0, because the input signal is 0 now, plus half the previous sample, which was the stored, delayed version of the impulse. So we took the impulse there and we put it in the delay, and now it's coming back, which also gives half. And now we move another one back. But the current input, as well as the previous one, are 0, so we now it's 0 out. So if we plot this output here with the input as a delta function, we get output y of n as 0.5 and 0.5 and zeros. So the impulse here has been smeared out a little bit, smoothened out, but it ends there. It's not continuing anymore. Let's see what happens if we look at the feedback filter instead. So now we're taking the impulse here, and at time, I'm going to remove this just to not confuse you. So now we're doing the feedback. And we're feeding it with an impulse. The impulse has just 1 at time 0, otherwise not. The output here at time 0 becomes then the input at the time 0, which is 1. And here we have a generic coefficient. I just wrote b. So we add b to the 0, because that's the previous output signal, and that was nothing. So the output is 1. Y for the next sample part. Now we take the input signal, which is now 0. The unit impulse has stopped being anything else than 0. So we add to that the delayed version of the output, and with a multiplication of b. And the previous version of that was 1. So here you have output 1. Next example, the same thing here. The input signal is 0. The output signal is b. But we have a multiplication of that also. So we get b squared. Point 3, input signal is still 0, but you can see that the output signal keeps on feeding back into the delay and coming back. And what you notice also is now it has a danger of increasing. So the value of this b, the value of this coefficient, that is how much of the output signal that you're feeding back, you need to choose carefully. In fact, it should never be 1. It should always be less than 1. Otherwise, your output signal is going to explode. And that's the essence of feedback filter or infinite impulse response filter.